Every year, something extraordinary happens all across our planet, completely unnoticed. More than 5,000 tons of dust from space settles over the Earth. It lands on our rooftops, dissolves in our oceans, and yes, in this very moment, you're breathing some of it in. This isn't the ordinary stuff that gathers in the corners of your home. This is something far more ancient and profound. It's cosmic dust, a mixture of material from comets and asteroids, and the microscopic remnants of long-dead stars. And within these tiny, almost imperceptible grains lies a secret. The secret to the brilliant stars in our night sky, the secret to the planet beneath our feet, and the secret to how everything we know, including ourselves, came to be. For much of astronomical history, this dust was seen as a nuisance. It was a cosmic fog that frustratingly blocked our view of distant galaxies. But we were looking at it all wrong. We've since discovered that this dust isn't just an obstacle to the story of the universe. This dust is the story. It's the tale of the invisible yet essential force that builds our cosmos, one microscopic grain at a time. Let's explore how these tiny particles, little more than cosmic soot and sand, serve as the grand architects of everything we see. When you hear cosmic dust, it's easy to picture the gray fluff on a bookshelf. The reality is far more spectacular. Cosmic dust isn't one single thing. It's a complex collection of solid particles, most smaller than the width of a human hair, that drift through the immense voids between the stars. Think of it less like household dust and more like a fine, pervasive smoke. This cosmic smoke is made of a rich variety of materials. At its core are silicates, the same family of rock-forming minerals that make up most of Earth's crust. It also contains carbon-based materials, essentially a form of cosmic soot, along with flecks of iron and nickel. In the deep cold of space, these grains often wear a delicate coat of ice made from water, ammonia, and methanol. And this dust is, quite literally, everywhere. The space between stars might look like a perfect vacuum, but it's actually filled with a thin mix of gas and these dust particles, known together as the interstellar medium, or ISM. Although dust makes up only about 1% of the ISM's mass, its influence is monumental. It drifts through the spiral arms of our Milky Way, chokes the hearts of distant galaxies, and forms vast dark clouds so dense they completely block the light from stars behind them. This created a real puzzle for astronomers. For centuries, they were frustrated by the dust precisely because it hid parts of the universe from view. A famous example is the Horsehead Nebula in the constellation Orion. That iconic dark shape isn't an empty patch of sky. It's a colossal wall of cosmic dust so thick that it obscures the brilliant stellar nursery glowing behind it. It's a cosmic silhouette. For a long time, this was seen as a curse, preventing our telescopes from peering into the most active regions of space, like the places new stars are born. But here's where modern astronomy changed everything. It turns out these tiny grains are incredibly efficient at absorbing visible and ultraviolet light from stars. That energy has to go somewhere. The dust grain warms up just a little and radiates the energy back into space, but at a much longer wavelength. Infrared light. Our eyes can't see in infrared, but our most advanced telescopes can. This single fact revolutionized our view of the cosmos. It means the very same dust that creates those dark, obscuring clouds is also shining with its own faint heat. When observatories like the Herschel Space Observatory and the James Webb Space Telescope, JWST, turn their infrared eyes to the sky, the veil is lifted. Suddenly, we can see through the dust and into the heart of stellar nurseries, witnessing the birth of stars and planets. The nuisance became our greatest tool. The dust is no longer a barrier, it's a beacon, illuminating the hidden processes of cosmic creation. Every grain of cosmic dust drifting in the interstellar void is a survivor, a refugee from one of the most violent events in the universe, the death of a star. To understand what cosmic dust is, you have to understand where it comes from. The universe didn't begin with dust. After the Big Bang, the cosmos was almost entirely hydrogen and helium. Every other element, the carbon in our cells, the oxygen we breathe, had to be forged inside stars. And it's from the ashes of these stellar forges that cosmic dust is born. The story starts with stars that live relatively gentle lives like our own sun. For billions of years, they fuse hydrogen into helium. But as they run out of fuel, they enter a dramatic new phase, swelling into red giants. In a late stage, known as the asymptotic giant branch, AGB, The star becomes a vast, unstable giant, cooking up heavier elements like carbon and oxygen. The star's grip on its outer layers weakens, and a slow, steady stellar wind blows this new material out into space. As this cloud of freshly forged elements expands, it cools. Once the temperature drops below about 2,200 degrees Fahrenheit, the gaseous elements can condense into solid particles, much like water vapor forms ice crystals on a cold window. Atoms of carbon and silicon clump together, forming the first seeds of dust grains. These AGB stars are the primary dust factories in the universe today, gently puffing out clouds of carbon and silicate dust. But the universe has a much more spectacular way to make dust. This is the domain of massive stars, behemoths more than 8 times the mass of our sun. These stars live fast and die young. Their cores are immense pressure cookers, forging elements all the way up to iron. When their fuel is spent, they don't fade away. They die in a cataclysmic explosion, a supernova. For a brief time, a single supernova can outshine an entire galaxy. The blast is so powerful that it forges all the elements heavier than iron, gold, silver, uranium, and hurls them into space at incredible speeds. In the cooling debris of that explosion, dust grains condense with astonishing speed. Supernovae are messy, violent, and absolutely crucial, especially in the early universe, where they were the main source of the dust needed to kickstart the formation of the first galaxies. For a long time, AGB stars and supernovae were considered the whole story. But recently, the James Webb Space Telescope introduced a new character, Wolf-Rayet stars. These are incredibly massive, hot stars, famous for their powerful stellar winds. It was thought these environments were too harsh for dust to survive. JWS proved that wrong. In 2022, it captured a breathtaking image of a Wolf-Rayet star named WR140, showing magnificent concentric shells of dust expanding outwards. It turns out that when WR140 and its binary companion star get close in their orbit, their stellar winds collide, compressing gas and providing the perfect conditions for carbon to condense into soot. Each orbit creates a new shell, a new plume of dust. This was a revelation. Another major source of the carbon dust that's a key ingredient for life was hiding in plain sight. For a long time, AGB stars and supernovae were considered the whole story. But recently, the James Webb Space Telescope introduced a new character, Wolf-Rayet stars. Once forged and cast into space, cosmic dust embarks on its next great purpose, to serve as the midwife for new stars. Without these tiny grains, star birth as we know it simply couldn't happen. The birth of a star is a battle between two forces, the inward pull of gravity and the outward push of gas pressure. For a star to form, gravity has to win. Cosmic dust is what tips the scales. The stage for this drama is a giant molecular cloud. These are colossal, cold, dark structures, spanning hundreds of light years. Inside, the main ingredient is hydrogen gas. But for a star to ignite, hydrogen atoms need to pair up into stable molecules, H2. In the vacuum of space, this is incredibly difficult. That's where dust plays its first critical role. It's a cosmic matchmaker. A dust grain provides a solid surface for wandering hydrogen atoms to land on. Once there, they can easily find each other, form a molecule, and then get released back into the cloud. Without dust grains, this process would be so inefficient that very few stars would ever form. But the dust's job isn't done. As gravity pulls a cloud of gas together, the gas heats up. This heat creates pressure that fights against gravity. If the cloud gets too hot, the collapse will stop. Cosmic dust comes to the rescue again, acting as a giant cooling system. The dust grains absorb the heat and re-radiate it away as infrared light, which easily escapes the cloud. By bleeding heat away, dust allows gravity to maintain its grip and continue the collapse. Over thousands of years, a dense spinning core of gas and dust forms at the center, a protostar. It's not a true star yet, fusion hasn't started. It's just a hot growing ball of gas. As the material collapses, it spins faster, just like an ice skater pulling in their arms. This rotation flattens the surrounding material into a vast, swirling disk of gas and dust around the protostar's equator. This is a protoplanetary disk. The young star continues to feed on this disk, growing in mass and density. Finally, after millions of years, the pressure and temperature at the center becomes so immense that nuclear fusion ignites. A star is born. Its newfound light and stellar wind blow away the remaining dust from its cocoon, revealing it in all its glory. and surrounding it is the spinning disk where the next part of the story begins. The birth of a star is a magnificent event, but for the cosmic dust that made it possible, the work isn't over. Orbiting the newborn star is the protoplanetary disk, a spinning platter of gas and dust containing the complete set of instructions for building entire worlds. Inside the disk, dust grains and gas orbit the young star. But the gas moves a bit slower than the dust, creating a kind of headwind. This drag causes the dust grains to spiral slowly toward the star. As they drift, they begin to collide. At first, tiny grains stick together through electrostatic forces like static cling, forming fluffy clumps that look like cosmic dust bunnies. But getting from a pebble-sized object to a kilometer-wide planetesimal is a huge leap. It was a major puzzle for a long time. Nature, it seems, has a few clever solutions. A key one is ice. In the outer part of the disk, far from the star's warmth, lies the frost line. Beyond this line, it's cold enough for water and other compounds to freeze onto the dust grains. These icy coatings are sticky. When two icy pebbles collide, they are far more likely to fuse together, dramatically speeding up growth. This is why the giant planets in our solar system, Jupiter, Saturn, Uranus, and Neptune, all formed in the cold outer regions. They started as giant, dirty snowballs. Another helping hand comes from complex organic molecules that form on the dust grains themselves, creating a sticky coating that helps them clump together. As these pebbles accumulate, another process called the streaming instability can kick in. Pockets of pebbles can become so dense that their collective gravity pulls them together, causing them to rapidly collapse into asteroid-sized bodies. These are planetesimals, the first true building blocks of planets. Once planetesimals form, the final stage begins. The disk is now a shooting gallery. The biggest planetesimals grow the fastest, their gravity sweeping up smaller objects. In the warm inner disk, this process built the rocky planets, Mercury, Venus, Earth, and Mars. In the outer disk, the cores grew much larger, gobbling up rock and vast amounts of ice. Once they reached about 10 times Earth's mass, their gravity became strong enough to pull in huge amounts of hydrogen and helium gas, creating the gas and ice giants. This whole incredible process is no longer just a theory. With observatories like the Atacama Large Millimeter Submillimeter Array, ALMA, we can now peer into protoplanetary disks around other young stars. And what we see is breathtaking. Clear gaps and rings carved out by newly forming planets as they sweep their orbits clean. For the first time, we are watching other solar systems in the very act of being built. The journey of cosmic dust forges stars and builds worlds. But its story may have one final, even more profound chapter. Could this same dust be responsible for the origin of life itself? Evidence is mounting that these humble grains aren't just inert specks of rock, but are tiny, floating chemical labs that create and carry the molecular precursors to life across the cosmos. A significant fraction of cosmic dust is made of complex organic compounds, molecules built around carbon. These organics form in cold, dark clouds long before a star is even born. On the icy surfaces of dust grains, simple molecules get trapped. Bathed in faint ultraviolet light from distant stars, they break apart and recombine into more complex structures. Over millions of years, this slow chemistry can build an inventory of surprisingly complex molecules, including sugars and even amino acids, the building blocks of proteins, which are essential to all life on Earth. So, when a protoplanetary disk forms, it's not just seeded with rock and ice, it's preloaded with these vital organic molecules. The dust grains that build asteroids and comets carry this precious cargo with them. In the early, chaotic days of our solar system, Earth was battered by comets and asteroids during a period called the Late Heavy Bombardment. This was a violent time, but it may have been the ultimate delivery service. Each impact could have delivered water and these complex organic molecules to the surface of our young, barren planet, providing the essential starter kit from which biology could emerge. The proof for this isn't just theoretical. We have tangible evidence. When meteorites, fragments of asteroids, are analyzed, they reveal a treasure trove of extraterrestrial organic compounds. The famous Murchison meteorite, which fell in Australia in 1969, contained over 100 different amino acids, many of which aren't used by life on Earth, confirming they came from space. And NASA's Stardust mission flew through the tail of a comet, captured dust particles, and returned them to Earth. Analysis confirmed the presence of organic material, providing a direct link between comets, dust, and the building blocks of life. This means the story of cosmic dust is, quite literally, our own origin story. The iron in our blood and the calcium in our bones were all forged in the heart of a star and traveled through space as a grain of dust. But the connection may be even deeper. The very molecular structures that our biology is built on may have gotten their start on the frozen surface of a dust grain, in a dark molecular cloud, billions of years before the Earth even existed. Our understanding of cosmic dust is constantly evolving, with every new observation from telescopes like JWST revealing another layer of the story. It's an incredible narrative showing just how deeply our existence is tied to the great cycles of the cosmos. If you want to follow along with these discoveries, please consider liking this video and subscribing to the channel. Let us know in the comments what aspect of cosmic dust you find most fascinating. We began with a simple fact, that dust from space is always raining down on us. We now see this isn't just a curiosity, but the final quiet act in a cycle of creation that spans eons. We've traveled from the fire of dying stars to the cold, dark nurseries where new stars are born. We've witnessed the patient assembly of planets, and considered that these same grains might have carried the seeds of our own existence. The dust that was once dismissed as an annoyance has revealed itself to be some of the most important stuff in the universe. It's the thread that connects galaxies to the molecules of life. It's the ultimate recycler, taking the ashes of one generation of stars and building the next. It is the quiet architect, tirelessly shaping the cosmos. So the next time you look up at the night sky, at the dark rifts that split the glowing band of the Milky Way, remember what you're really seeing. You aren't looking at emptiness. You're looking at the raw material of creation. Vast clouds of cosmic dust, the fertile soil from which new stars and worlds will one day bloom. And remember that you are a part of that story. The legacy of that ancient stardust isn't just out there in the cosmos, it's within you. We are, in the most literal sense, children of the stardust.